Now we have 35 minutes instead of the basic result of. So we want to have a new glance on old equations, and we are going to cast the Schrödinger equation in the matrix form. So the benefit of this procedure, and it can be considered either as a recasting Schrödinger equation as a set of individual equations for expansion coefficients, or we can just formulate it in form of a matrix equation for column vector. Any quick questions about homework? Or it seems okay? Or you didn't start? Please start at least today. It is not one night homework. 2 nights can be fine, but in last night, I will not be able to answer emails if you ask something. So try tonight and give me some time to answer your questions if you develop some. This one is mathematically challenging, and this one is most scary, but the results should look same way as you drop something, material object in real life. So this potential is set up to mimic the constant acceleration. So the result should be very easy to interpret. So we do not have anything new on this diagram, but we are expanding on time-dependent Schrödinger equation. We are making it in the matrix form. So if we will fail to finish in time, here is what I would like you to take as a take-home message. Instead of continuous function, we can represent wave function as a set of discrete expansion coefficients. It doesn't surprise you. And then we can set up an equation for this vector, or for each element of this expansion. And so we have time derivative of these coefficients on the left, time derivatives on the right, and here there will be a matrix that replaces Hamiltonian, or represents Hamiltonian. So instead of operator cast in the way of differential operators, it will be just set of numbers in the matrix. And solving time-dependent Schrödinger equation is equivalent to solving a set of first-order differential equations. First order differential equations. Make sense? So if you're fine with this idea, the rest will be technical details and some motivation why we need it, and some technical steps how to get this equation from what we have. Within the next couple of weeks, we will not see immediate benefits, but as time goes by, you may appreciate this piece of material. And these things are protocols, are ways how to find elements of this matrix. So in order to make this matrix, you need to select a basis. Typically, the most comfortable basis is the basis of eigenstates of Hamiltonian. But sometimes, especially if Hamiltonian may slightly change in time, then you select the major component of the Hamiltonian, find the eigenstates, and for them, for the states of eigenstates, you find this convolution of operator with functions, with basis functions, and they do help to formulate this equation. Done. It is what I was planning to say at the last minute of the meeting. If time allows, I will repeat, but I foresee that time will not allow. So, technical details. So, before now, we always had wave function. We know that one can represent wave function with a set of expansion coefficients. We actually need this expansion coefficients when we find time-dependent solution of Schrödinger equation, right? So our expansion coefficients is what makes a bridge from initial condition to the solution. So this concept is not completely new, but one can do all operations that we do here, all operations that allow to predict outcome of experiment. All operations that allow to predict future, allow to find observable propagation, time propagation observable. Everything can be done in the basis of this expansion coefficients and not touching continuous wave function at all. So this is a protocol for those who hate differential operators. So there is a way to avoid it. Avoid differential operators. And just to make our, well, I cannot make our life easier, but I can make our meeting here easier. We will assume that this infinite list of expansion coefficients stops at first and second, same as you do in homeworks. And if you get the main idea, there will be not a problem to get further. So, what do we do? Which mindset, which protocol did we develop in class? So we have some, well, not right now, but we are starting thinking this way, that one can look on an experiment, develop a model, find Hamiltonian, find solution for initial condition, and predict observables, and then compare the outcome of our modeling here in class with what you do in your research or in other experiments, or what we see from literature. So this protocol was thought to be pursued with the help of wave function, which is not wrong. It is by definition with wave function, but in order to avoid not necessary boring integration at each time step, integration of space or other variables, one can remove wave function from consideration at all. So this is the goal that we are pursuing. So our favorite object of interest is a replacement of wave function, which is a column vector of expansion coefficients. So for next 20 minutes, we focus on the column vector of expansion coefficients. From our previous life, or previous meetings, we know that sometimes one needs wave function in two forms, with and without star, when we are pursuing the protocol to find observables, right? And if we are jumping from continuous wave function to this discrete wave function, we need an analog of this wave function star, which will be rho vector. And if wave functions, eigenstates, do have property of orthogonality and orthonormality. There should be an analog of this in the work with vectors, which will be normalization that can be set as this row by column, and here this row with stars should give 1. So for any quantum state, even if it is represented by vectors instead of wave functions, there is a normalization condition. Normalization for continuous and for discrete. This is something you know for several weeks, or maybe longer. So that if you do know expansion coefficients and initial time, you can easily find them at any subsequent time, right? You can just plug in the time accumulation factor. In case these functions are eigenfunctions of Hamiltonian, then expansion coefficients will just propagate in a simple way. This here. And if you have this solution of Schrödinger equation, then we can, and we were in the past, finding observables, which are the goals of all of this activity, right? So we were taking conjugative wave function at each time, wave function itself, putting an operator of interesting observable, and we will work on developing a set of reasonable observables. There will be time for this. And execute it at each point of time. Okay? Now, if our wave function with star is a bra vector, and it is C1 star 1 plus C2 star. Wait, different. Where's my eraser? Bra. Operator. Cap. So I'm repeating something trivial that you have made several times during execution of homeworks, and maybe for your curiosity, or maybe from taking notes if you decide to do them. So by opening brackets, and again, why I'm opening these brackets? Because this yes, it's good to ask questions to yourself. So because it is main protocol for our main goal to find observables, and if you open these brackets, you will get C1 star C1 phi 1 A phi 1 plus the three other terms, right? First, middle, last. First, middle, last. Right? So if you run over different indices. But the time dependence, everything that changes with time, will be hidden in this product of expansion coefficients, right? And everything which is related to integration and finding matrix, everything related with integration will be hidden in the second term. Integration, which means that no matter how far we went in time. No matter what is happening in time domain, the integral here in this term will be always the same. And it will be extremely silly if you run for 1,000 steps to repeat the same integration for 1,000 times. Especially if number of basis states is small. You can just compute these integrals for this term and other once and forever, record them in the file, or just, if we do by pen and paper, just write a little table. If it is like a 2 by 2 matrix, we can write with the numbers. And then plug them in at each point of time. In fact, we'll start here. I'm going to scroll back to the homework, especially to those who haven't looked on it at all. It will be a great and hopefully positive surprise. So, if you look on the question number 2, and section number 3. So here there is a assignment to find observables as function of time. But as a hint to avoid boring integration, there is a suggestion to make this one first and find this matrix elements, the convolution between operator of interest and basis functions ahead of time. So you do it ahead of time, and then you use them here when you practice your prediction of future and finding observables as function of time. So if you have completed this homework, then you do not need this meeting. You already have all the ideas. So I'm just trying to mumble some basic views and background information that will make you comfortable to go through this procedure. Prepare to close the eyes and go with light speed quick to slide number X. I don't know what is X, but I've placed a little star in low right corner, so you should be able to recognize it. Yes, here. How would you call these things that we integrate once and forever? Just give signs if you have an idea how to call them. Okay. We are replacing wave function by vectors, and we are replacing operators by matrices. And those will be elements of the matrix that replaces an operator. So it would be not wrong to call it. Now, if you know, you can pronounce it out loud.
What?
How to call this object? Give some suggestions.
Eigenstate?
No, no. Eigenstate is this phi function.
Inner product?
Inner product is whatever when we have Bryant cap. It is correct, but too general. But more specific. If you have specific operator of interest,
The expectation value?
it is also correct. But again, expectation value, if there is a well, here is expectation value. If you have complete wave function of a state, which is not an eigenstate on the left and right, but if it is expectation value in basis of eigenstates or any basis states. So this is a protocol to convert matrix, convert operator into matrix. And those will be elements of this matrix. So I'm very uncomfortable with this term, but it is used everywhere. So this matrix element of operator A. Okay? In fact, in your homework, you are finding matrix elements of operator of position, matrix elements of operator of momentum. You take basis functions, you put operator in the middle, and then you find it, where the indices here and there can be different. Make sense? Good. I was just preparing ahead of time and typed it. So expectation value can be composed as adding together several terms. In each term, there is a time evolution, so these coefficients are carry time dependence, and things that carry the properties of operators and basis functions, convoluted. So matrix elements and time dependence. And laziness is an engine of a progress. Least action is the main principle of whatever we do or not do. 1, 2, 3, 4, 5, 6, 7, 8 objects. No, I would die to write them every time. So why don't we replace 8 symbols with 3 symbols? Like A, 1, 1. A, 1, 2. A, 2, 1. A, 2, 2. So matrix elements of a given operator serve towards completion of our goal of the destiny. Find expectation value. So justification why we need this matrix element. So in order to pursue our goal, we do not need wave function. We need matrix elements of an operator, and we need time dependence of expansion coefficients. That's it. We even do not need to plot how wave function looks like. And we do not need to know what it is. Expansion coefficients and matrix elements are sufficient. If you do some practical calculation, not for education, but for bread and butter. If we decide to go into the market of calculators, well, quantum calculators for physical chemistry, predictors of the future. Good? So we covered how to cast observables by wave function. There is an alternative way to cast observables by density metrics, which we covered in the past. I will try to jump through as quick as possible because it is auxiliary information. And then the most important thing will be to use main message that, let me repeat it, matrix elements and expansion coefficients. It is only what we need. So, in this conclusion technically allows us to jump to last section of the meeting, which will show how to develop equation for expansion coefficients. And for matrix elements, you already know how to find them and what they are. Just quickly for overview, there will be a little side thing. Okay, if you are watching it here's a verbalization, what we need and can do. And if you follow this prescription for each basis function, then an operator is replaced by a matrix of matrix elements. Okay. You already went through it. Expansion coefficients, matrix elements. Expansion coefficients, matrix elements. Nothing else. It's sufficient for getting the expectation value. And if you have only expansion coefficients and matrix elements, we may instead of this explicit formulation, we can write it down as row vector times matrix times column vector. Well, this silly image blocks it, but it will be C1, C2 column vector. Density matrix, please come. So it is what we defined, I think, in previous homework, when we looked on the probability distribution of non-eigenstate of particle in the box, 50% between first and second. And we discussed that one can pursue the dependence of the products of expansion coefficients, not as product of two functions, but as this objects called density matrix elements. If you do know them, you can also find expectation value at once. Here's a little definition from linear algebra. If you have a matrix, a trace of matrix is diagonal, summation of diagonal elements. So, lean back, relax, it is secondary information, not important. If you are taking notes, you can take your pen off the paper. So if you multiply matrix of this density matrix times a matrix that represents an operator, pursue this matrix multiplication in a careful way, and then find a trace of these elements on a diagonal, one would instantly recover that it gives the same outcome as we had 5 minutes ago. So matrix element times corresponding product of wave function expansion coefficients. Matrix element times product of wave function expansion coefficients, which prompts us that concept of matrix elements is useful in several protocols of finding expectation values, both through the immediate utilization of expansion coefficients or through density matrix. Why someone needs it? Because there are some methods that avoid computation of expansion coefficients and directly go into density matrix. So if you know it, you can multiply it by matrix representation of operator, take trace, and then you will get the expectation value. Done. And this trace, density matrix times matrix representative operator, expectation value. Now, most important part, for which you have 9 minutes. Wake up, please. We will get the first equations that we discussed on the board as an outcome of this overview and derivation. So, by now we agree that we do have matrix elements for operator of interest in observable. And the only missing thing are expansion coefficients. In trivial cases, if Hamiltonian is time independent, if it is easy to diagonalize, we can find expansion coefficients just by phase accumulation. But there are some situations when eigenstates are hard to find. And non-trivial situations for educational part are most typical for real life. So for real life, this equation of motion for expansion coefficients that we are trying to derive is most important. So you can safely get highest grade in the course if you do not want to have connection to real life. But if you want to see this connection, the working in specific basis is what everyone does. So we are going to merge together time-dependent Schrödinger equation, concept of expansion and expansion coefficients. And we will keep in mind that wave eigenstates, or even not eigenstates, just basis functions that we use obey not only orthogonality but orthonormality. So their convolution will give either 1 or 0. Okay? Trigger. Now we are going to practice this thing, plugging in the definition of expansion coefficients into Schrödinger equation. So our basis functions are chosen to be time independent. Most simplest example of basis functions are eigenstates of Hamiltonian. And even if there are some problems with finding them, we can select a set of basis functions that are comfortable to work with. And if their time independent, we can put them to the front of derivative operator. Phi1 times d dt c1 is phi2 d dt c2. All right? Equals same as was here. Very comfortable. We have a term for time dependence of expansion coefficients. But overall, this object is still a wave function because it has this wave function here and there. But we can apply a standard trick. We can use the orthonormality principle and multiply this expression by a basis function, by a cat from the left. I know that I'm doing the wrong thing. Cat is written in a different way. So, cat from left. And I want to be general. Instead of plugging in specific number, I will tell it will be wave function number m. Phi m multiplied by left. And here phi m multiplied by whatever is there. Why are we doing it? Because due to orthogonality, no, I was doing wrong. It's bra. No one corrected me. No one wants extra points, or no one is following. So bra from the left, right? So we already have. So we multiply bra from the left, and then due to orthogonality, these terms will convert into numbers. So instead of continuous functions, they will become numbers, number 1 or number 0. And through this trick, we will remove any memory of continuous functions from here. We will keep only continuous functions, functions of position. We will have only dependence on time, right? Time only. So it is where we are, multiply by bra from left, and make sure that we do not have time dependence of this expansion coefficients. What else is left? Plug in specific values of m. And in our case, we can plug m equals 1, m equals 2, and see how this equation will change. So if m equals 1, then this convolution becomes 1, second convolution becomes 0, right? And if m equals 2, then this convolution becomes 0, this becomes 1. And then instead of one equation, we will have how many?
Two equations.
Two equations. So we are replacing the bra and cat convolutions into 1 or 0. So we replace either to 1 or to 0. And through this trick, we will parse only one expansion coefficient on the left. So if m equals 1, then only C1 survives and the rest are dead. If m equals 2, only C2 survives and the rest are dead. Okay? And on the on the right side, we were plugging in m equals 1 here and there. And you see that there is a convolution of matrix element times expansion coefficient. We are almost done. Now we can realize that this can be considered as a column vector, and this is implementation of this matrix by this column vector. Right? Expansion coefficient C1 and C2, expansion coefficient C1 and C2, and the matrix elements of Hamiltonian operator. So there are two types, matrix elements of our operator of interest and matrix elements of Hamiltonian operator. And if you know them, they drive time propagation of the expansion coefficients. Thanks for coming. Looking forward to see you on Wednesday. We'll stay ready to answer emails about homeworks. And please consider to bring printed homeworks to the class on Wednesday. Good evening.